Hey everybody, welcome to our next Calculus 1 lecture. And this time we're going to introduce continuity or continuous functions. And to set the tone for this, let me just ask you something. Suppose I came in one day and I looked real tired. I said, I didn't get any sleep at all last night. My neighbor's dog barked continuously. Well, we've probably all had a neighbor like that, haven't we? And if I say my neighbor's dog barked continuously, the sense that a person would get from that is that the dog barked without interruption. Bark, 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 bark. Well, continuity, or the word continuous in math, believe it or not, has a very similar connotation. If we talk about a continuous function, we're talking about a function whose graph goes on and on and on without interruption. So a continuous function is a function whose graph has no interruptions, no breaks. So let's just write that down. Oh, I hope I spelled that right. If I spelled that right, that's definitely going to be a first for me. But intuitively, this pretty much tells us what a continuous function is. It's a function whose graph has no breaks or interruptions. The graph is one long connected piece of spaghetti. So let's see, maybe some things we can underline here. The graph is one piece only. The graph is one connected piece. So there are no unconnected pieces of the graph floating around anywhere. The graph is one connected piece, which means that you can put your pen on any point on the graph and move along the graph with your pen and get to any other point on the graph without leaving the graph itself. So the graph is one long connected piece of spaghetti, no breaks, no interruptions. And the first thing that we want to do in our coverage of continuous functions is just get to know what continuous functions look like and what the graphs of functions that are not continuous look like. By the way, if a function is not continuous, that we say that it is discontinuous. Just like if I don't pay my subscription to a service, they will discontinue my service. I have an interruption in service. So hopefully I remember to pay all my bills. But anyway, our first objective is to make sure that we know the graph of a continuous function when we see it, and also that we recognize the graph of a discontinuous function when we see it. If we can do those things and we can distinguish between one and the other, then we've accomplished our first objective. So let me put some graphs on the board and we'll look at each one carefully, okay? Okay, here's our first set of examples. Let's take a look at the first one right here. What would you say? Would you say that f of x is continuous or discontinuous? And to answer that, maybe we'll look at it and say, do I see any breaks or interruptions in the graph? Now the graph does come to a sharp point right here, but does the graph actually break into two separate pieces here? I don't see that it does. So what would you say? Continuous or discontinuous? If you say continuous, I'm inclined to agree with you. It looks like this graph is one connected piece, one long connected piece of spaghetti. So our vote is for continuous. And we'll give a reason. It's one connected piece of spaghetti. The graph consists of one piece, and it's connected. The graph isn't broken into two separate pieces, or three separate pieces, or four separate pieces. This graph is one connected piece, it's continuous. Now let's get on to the second graph. We've got some vertical asymptote action going on here. What would you say here? Continuous or discontinuous? And I guess one of the things we'd look at is, are there any breaks or interruptions in the graph? And right now you're probably thinking, well, right here at x equals 4, it looks like the graph breaks into two pieces. There's one piece to the left of x equals 4, a different piece to the right of x equals 4, and they're not connected. And if you're making that observation, you're right. So here's what we would say. The graph is discontinuous at x equals 4. And to justify our answer, we might say something like, the graph is two separate pieces. Or maybe something else that we could say, this is a good answer. What I'm about to write is a good answer also. There's a break or an interruption at x equals 4. So here's my justification for saying that the graph is discontinuous at x equals 4. One answer I can give is that the graph is two separate pieces. Here's one piece, here's the other piece. They're not connected. Another good answer is I can say that there's a break or an interruption in the graph right here at x equal 4. So either of those are good answers. Now, this guy right here, this graph, what do you think? Continuous or discontinuous? And if we say discontinuous, then it would have to be because we see a break or an interruption in that graph. Do we see a break or an interruption in this graph? I don't. It looks like here I can take my finger and move along this graph and never lift my finger off the graph and move from one point on the graph to any other point on the graph without lifting my finger. One connected piece. So I think our vote here is going to be for continuous. And we got to have a reason. The graph is one connected piece. Now, I guess I'd like to look at one or two more graphs, just so that we're accustomed to seeing all different kinds of scenarios. So let's look at a couple more examples before we try to formulate a mathematical definition of continuous. Okay, we're back with some more examples of continuous and discontinuous functions. Let's look at this thing. Is it continuous or is it discontinuous? Now, probably you're looking at this and saying, well, here's one piece of the graph here. Here's another piece of the graph here. And the two pieces are not connected. There's a big interruption right here, or a big break right here. And if you're looking at that and saying this graph is discontinuous because there's a big break here, or the graph has two separate pieces, you're absolutely right. That's exactly how we're going to diagnose this. So, f of x is discontinuous. And we'll say it's discontinuous at x equal 3 because that's where the break occurs. And we have to give our reasons. There's an interruption. There's an interruption or break at x equal 3. This is a good reason. Now we might also say, or alternatively we might say, the graph consists of two separate pieces. And that's another good reason. Either one of these reasons is good on their own. So the graph consists of two separate pieces. So either one of these answers is a good justification for saying that f of x is discontinuous. Now let's look at this example. We might be hesitant because it almost looks like this piece and this piece join together at x equal 3, but we're not going to commit ourselves to saying that because we see this open circle here, which means that this is not a point that's on the graph. And if that's what we're thinking, we're right. How was this graph formed? Apparently, this was all one connected piece at one time, and then somebody came along with a pair of tweezers and they plucked this point out and put it up here. And so now this piece and this piece are not connected. They're separated right here at x equal 3, where I took my tweezers and I plucked out that point and put the point up here. So I guess we really do have an interruption at x equal 3, don't we? There's the point that would connect this part of the graph with this part of the graph is missing. The point that should connect these two pieces has been removed and it's been put up here. So here's what I'm going to say. I'm going to say f of x is discontinuous at x equal 3. And I have to give my reasons. See, what's my first reason? There's an interruption or a break at x equal 3. On its own merit, that's sufficient to justify our diagnosis that this function is discontinuous. We definitely do have an interruption. The graph goes from here to here. Now, the other reason, let's see, is the graph one connected piece? Now, how many separate pieces would you say this graph is made up of? I'll tell you what I think. I say this is one piece, this is another piece, and this is a third piece, and they're all separate from one another. So I'm looking at this graph and I'm saying this graph is not two separate pieces, it's three separate pieces. So that's going to be my alternative explanation for why f of x is discontinuous. The graph consists of three separate pieces. So now I think we've achieved our first objective. I think we know a continuous function when we see its graph. We know a discontinuous function when we see its graph. And we definitely know how to distinguish between one and the other. So our first objective has been accomplished. We know a continuous function when we see one, and we know a discontinuous function when we see one. The next thing that we're going to do is we're going to give a mathematical formulation of continuity. Back again. To mathematically formulate the concept of continuity or continuous function, we have to start off with the idea of a function being continuous at a point, a single point, x equals c. And the definition here says that f of x is continuous at a point x equals c exactly when this holds true. Exactly when the limit as x approaches c of f of x is equal to f evaluated at c. Now, how does this thing convey the idea that a continuous function doesn't have any breaks or interruptions? A continuous function is all one connected piece of spaghetti. It's not at all obvious what this statement has to do with our graph having or not having breaks or interruptions in it. So to get an idea of why this criterion is relevant, let's consider how it might be possible for a function f of x to fail to be continuous at a point x equals c. I'm going to write this criterion down again, right down here. Limit as x approaches c of f of x is equal to f evaluated at c. I'm writing it down here just so that we'll have it to look at for reference. I just barely squeezed it all in. And maybe the best thing to do is take a look at functions when this criterion fails to hold, or when a function fails to be continuous at the point x equals c. If a function is continuous at the point x equals c, that means that this condition holds. And if this condition holds, then the function is continuous at the point x equals c. So if the function fails to be continuous at the point x equals c, that means that this equation doesn't hold. Well, what's the first thing that could go wrong? It is an equation, right? And an equation has two sides. So maybe the thing that goes wrong with this equation and that causes it not to be an equation is something goes wrong on the left side. The limit as x approaches c of f of x. Well, what could possibly go wrong here? And maybe what could go wrong here is that this limit doesn't exist. If this limit doesn't exist, then the left side isn't defined, and it certainly can't be equal to the right side. So maybe the reason that this equation might not hold is that something goes wrong on the left side of the equation. The limit doesn't exist. So that's the first thing that can go wrong. So that's what can go wrong on the left side of the equation. But maybe this limit does exist. Maybe the problem is not here on the left side of the equation. Maybe the problem is here on the right side of the equation. Maybe this thing doesn't exist. That would certainly make it impossible for the left side and the right side to be equal, right? So maybe f evaluated at c doesn't exist. It's just not defined. So that's the second thing that can go wrong. So if this equation doesn't hold, it might be because something goes wrong on the left side of the equation. Or it might be because something goes wrong on the right side of the equation. Or maybe everything's fine on the left, everything's fine on the right. Maybe the problem is right here. Maybe this exists, but they're just not equal. So that's the third scenario. So those are the three reasons why a function may fail to be continuous at the point x equals c. Now that still, in my mind, doesn't tell us how the criterion for continuity at a point has anything to do with breaks and interruptions in a graph. So let's look at this graphically. But we'll make an example out of this. Let's look at each one and see what it indicates about the graph of f of x. And we'll start with this one. The limit of f of x as x approaches c does not exist. Okay, hopefully we took our memory pills this morning. What goes hand in hand with, quote, the limit, end quote, of a function not existing? What goes hand in hand with the limit, that is, with x approaching from either direction? What goes hand in hand with the limit not existing? And if you don't know what I'm talking about yet, let's look at it from the opposite perspective. What goes hand in hand with this limit existing? See, quote, the limit of f of x as x approaches c from either direction exists exactly when what? You got it? Exactly when the two one-sided limits are equal, right? And in that case, quote, the limit of the function, end quote, has the same value as the two one-sided limits. Now, if this limit doesn't exist, if, quote, the limit of f of x, end quote, doesn't exist, that means that the two one-sided limits are not equal. Okay, let's look at that. If, quote, the limit, end quote, doesn't exist, it's because the two one-sided limits are not equal. So let's just make up an example. Okay, those two one-sided limits aren't equal. Let's take a look at this graphically. Here's C. Here's the origin. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this one-sided limit tells us that as x approaches c from the left, f of x, the y value, gets closer and closer to 2. Well, here's x equal 2 on our graph. So as x approaches c from the left, let me put a 2 here. Okay. As x approaches c from the left, the graph is going to get closer and closer to this line. Now, the graph may approach the line y equal 2 from below, or maybe the graph approaches the line y equal 2 from above. Doesn't matter, let's just pick one. Let's just say that the graph approaches y equal 2 from above. So, as x approaches 2 from the left, the y value approaches 2 also. I'm sorry, I didn't say that correctly. As x approaches c from the left, the y value, excuse me, approaches 2. Oh my goodness. As x approaches c from the left, the y value, f of x, gets closer and closer to this line, y equal 2. And the two things happen simultaneously. So x approaches c from the left, and y equals f of x gets close to 2. So the graph comes down like this. Okay. Now, this limit says as x approaches c from the right, f of x, the y value, gets close to 10. Now, as x approaches c from the right, f of x, the y value, may approach 10 from below, or f of x, the y value, may approach 10 from above. Could happen either way. Let's say that in this case, f of x, the y value, approaches 10 from above. So as x approaches c from the left, f of x, the y value, is approaching 10 from above. And both of those things happen simultaneously. So here's x moving from right to left, approaching c from the right. And as it does, the graph of f of x gets closer and closer to y equal 10. As x approaches c from the right, y approaches 10. As x approaches c from the left, the y value approaches 2. Both of these one-sided limits hold. And what do we notice about the graph? There's a break or an interruption at x equals c. And this is a pretty big break or interruption, isn't it? Now we could also point to something else. The graph is not one connected piece, is it? One piece is down here, one piece is up here. So we might also mention this. The graph is two separate pieces. And that's what happens when the limit of f of x as x approaches c doesn't exist. If this limit doesn't exist, then the two one-sided limits can't be equal. And that causes our big break in the graph. So that's the graphic depiction of the first scenario, where the limit of f of x as x approaches c just doesn't exist. Now let's look at a graphic depiction of the second scenario, where f evaluated at c doesn't exist. And there's probably a couple of different ways we could approach this. Okay, here's the second scenario. F evaluated at c doesn't exist. And here's a look at one way that this could happen. The limit as x approaches c of f of x equals infinity, and f of c isn't defined. Now, let's draw a graph of what that looks like. Here's x equals c. And this says as x approaches c from either direction, f of x, the y value, is going to go to infinity. So here's x approaching c from the left. And as it does, f of x, the y value, goes to positive infinity. The net effect of both of these things happening simultaneously is that the graph goes from left to right, and it goes up like that. Now, as x approaches c from either direction, y equals f of x goes to infinity. So that also means that as x approaches c from the right, f of x, the y value, goes to positive infinity. And the net effect of both of these things happening simultaneously is that the graph goes from right to left, and it goes uphill like this. But right here at x equals c, there's no point on the graph, is there? So this piece of the graph and this piece of the graph are separate pieces. We have a break in the graph at x equals c. Definitely a break in the graph. There's also something else we could notice. This piece of the graph and this piece of the graph are separate. The graph consists of two separate pieces. And this is a result of f of c being undefined. Now let's look at the remaining scenario. Okay, here's the third thing that can go wrong, along with its graphic depiction. The limit as x approaches c of f of x exists, and f evaluated at c exists. They're just not equal. Now let's get a graphic depiction of this. Let's suppose that the limit as x approaches c of f of x is equal to 2. And let's suppose also that f evaluated at c is equal to 6. Okay, these two things are not equal. Let's draw a graphic depiction of that. Here's x equals c. Here's the origin. Here's 1, 2, 3, 4, 5, 6. This statement says, as x approaches c from either direction, f of x, the y value, is going to get close to 2. So here's the line y equal 2. And as x approaches c from the right, f of x, the y value, is going to get close to 2. So the graph is going to get close to this line. Does the graph approach this line from above, or does it approach from below? It could happen either way. For the sake of example, let's just say that as x approaches c from the right, the graph of f of x approaches the line y equal to from below. So as x approaches c from the right, f of x, the y value, approaches c from below. And as x approaches c from the left, let's say that f of x also approaches 2 from below. So the y value, f of x, approaches 2 through values that are less than 2. So here's x approaching c from the left, and here's f of x approaching 2. The graph will go from left to right and up toward 2 like this. Okay, that looks easy enough. But this limit only tells us what f of x does as x approaches c. Remember, when we're computing the limit of f of x as x approaches c, we can make x as close to c as we want, but we also stimulate that x never actually becomes equal to c. So based on this statement alone, we can't really say what happens right here at x equals c. But this statement does tell us what happens at x equals c. This statement says when x equals c, f of x, the y value, equals 6. So let me plot that. Here's x equals c, and here's f of x, the y value. So x is c, and the y value, f of c, is 6. So when x equals c, f of x is not equal to 2. So we've got an open space right here. This is one of those tweezer graphs where the point was here, but somebody took a pair of tweezers and plucked this point out and moved it up here. Oh my goodness. So when the limit of f of x exists and f of c exists, but they're not equal, this gives us an idea of what the graph looks like. And there is an interruption in the graph right here at x equals c. The graph jumps from 2, the graph jumps from y equal 2 to y equals 6. So there's an interruption or break in the graph at x equals c. Now there's another way that we can look at this graph to support our claim that the function is not continuous. And what we do is we count the number of separate pieces. Are there more than one? Well, these two pieces are separated by this missing point right here. This is one separate piece, this is two separate pieces, this is three separate pieces. So, the graph of f of x consists of three separate pieces. So this is what we've seen. We've seen three graphic depictions of what happens when this condition does not hold. And we want to recollect just exactly what it was that we saw that happened to be common in all three depictions. What's one thing that happened to be true in all three depictions where this condition didn't hold? There was always a break where? At x equals c, right? In all three cases, there was a break or interruption at x equals c. Now, what else happened to be true in all three depictions? Think back. What else happened to be true in every depiction? Separate pieces, right? That's right. So in all three cases, there were at least two, maybe more, at least two separate pieces. And just for emphasis, no, this is what happens when the condition limit as x approaches c of f of x is not equal. No, I won't do it that way. I'll say limit as x approaches c of f of x equals f of c does not hold. And what is the case when this does hold? No breaks or interruptions. Graph is one connected piece. Now, we will continue on with this tomorrow. But today, we have gained an intuitive idea of what the graph of a continuous function looks like and what the graph of a discontinuous function looks like. And we know how to distinguish between one and the other. And we have begun to formulate mathematically the concept of continuity and continuous function by using this criterion, continuity at a point. We've seen what happens when this condition doesn't hold. We get breaks in the graph. The graph is two or more separate pieces. When this condition does hold at every single point on the graph, then the graph is one connected piece, no breaks or interruptions. And we are going to follow that up in the next lecture.